Let's see now how to move from applying somewhat blindly these regression models to really trying to think about the classification problem in the way that we want to in terms of these discrete class labels. All right, let me write a more general version of the linear model that we saw in the previous session. Remember in the previous session we said that our output, our class label y, was going to be a linear combination of the inputs, and I just had two inputs because I was in a two-dimensional space. Let me write this in terms of an arbitrary dimensional space of dimension m. So I'm going to have that constant term here because I don't know where the offset of all the values are. And then I have w1 times x1. x1 is the first dimension, if you will. x2 is the second dimension. xm is the last dimension. And wm down to w0 are my model parameters that I want to estimate from a labeled training set. Let me take this and write it in a slightly more compact way because that's a little cumbersome to lug around. Notice what I'm doing here is I'm taking a dot product between two things. Let's ignore the w0 for a second. I have a vector w1, w2 up to wm. I have another vector x1, x2 up to xm. W are the model parameters. X are the data input. And if we think of those as two vectors, I'm going to just take a dot product. I have W as a row vector, X as a column vector, and I take a dot product, so I'm going to sum the pairwise product. And that's what I'm writing right here. The sum from I equals 0 to m is this where I'm going to assume that x sub 0 is equal to 1. So I don't want to lug around this extra term, so I'm going to assume there's an x0 there. I'm going to hardwire that to 1 every time, the same way we did when we did line fitting, the same way we just did in the previous example. And now I can write my model as just the dot product between two vectors, the unknown weights, the model weights, and the data that is actually coming in x, where I've said that the first parameter is going to be 1. And that's just a little bit more compact notation, so we don't have to lug around this big sum here. Okay. Now, the problem with this before was that, y could be anything. We had no control over it. Let's think about this really beautiful nonlinearity, the sigmoid. By the way, we've seen the sigmoid before. Where did we see it? When we were doing contrast enhancement in the beginning part of this class, where we were taking gray values and mapping them into new values and doing this contrast enhancement. The sigmoid is going to make a comeback here, and it's going to make a comeback when we start talking about artificial neural networks as well. Here's the functional form of a sigmoid. It's 1 over 1 plus e to the minus z. So f of z is the function of the sigmoid. And there are actually some parameters here where I can control, and we saw this when we did contrast enhancement, I can control the steepness of this, and I can control the offset. For now, we'll just fix those parameters to be 0. You can see that this is centered at 0, and then a unit slope. We won't worry about those parameters right now. So this is the sigmoid that I'm plotting here. And let's think about what happens when z, the parameter to the sigmoid, is w transpose x, the output of this model that we have right here. All right, well, before, when we did least squares, what was happening? We were getting things that were sort of 1 and sort of 0, but they would sometimes get bigger than 1 and sometimes less than 0 because the least squares in the regression had nothing to say about bounding the output. But imagine I take those values that we used above, greater than 1, less than 0, and I shove them into this sigmoidal nonlinearity. What is going to happen? All right, so this axis here is y. It's w transpose x. And it's going to be pushed through a nonlinearity that does what? Well, it caps the max value at 1 because it plateaus here, and it caps the min value at 0. Oh, that's sort of interesting because that means that I can never get a value greater than 1, and I can never get a value less than 0. Now, I can still get floating point values in the middle here, right? There's no guarantee that I have an absolute 1 and an absolute 0, but at least I've sort of solved my problem from the top and from the bottom now. So let's see how this works and how this comes together in what is called logistic regression. And you can think about logistic regression as basically a version of least squares where you have a sigmoidal nonlinearity that bounds the results of your output to be guaranteed 0 and 1. Now, the other way you can think about the sigmoidal nonlinearity is as a probability. If I have something that is bounded between 0 and 1, that sounds a lot like a probability. What's the probability of something happening? It has to be between 0 and 1. And that's in fact how we're going to formulate logistic regression in this version of building a classifier from this linear model. So consider the following. Let's think about the output of that sigmoid on our model applied to the data as the following probability. What is the probability that the class label is 1 given some input x? Remember that the vector x is your input and that the vector w is the model parameters and y, of course, is your class label. We have two labels, y equals 1, y equals 0. So I'm going to think about f of a w transpose x, model parameter shoved through the sigmoidal nonlinearity, as the probability that the class label is 1. So when this is high, when this returns 1, it has a high probability of being 1. And the probability that y is 0, the other class, is just going to be 1 minus that. Because if that's 1, well then 1 minus 1 is 0, and I've got my other class label. All right, so now what we're doing is we're thinking about that sigmoidal as not just bounding things, but we're thinking about it as an actual probability because the outputs are bounded between 1 and 0, and so we can think about them as probabilities. All right, now what I want to do, let me go back up one here. What I want to do now is I'm sort of getting to that place where I have an objective function, and eventually we're going to get to a place where we want to minimize it. So, but what do I want to do? I want to maximize or minimize something, right? I want to maximize the probability, let's say. So I want to maximize the probability that this is 1, and I want to maximize the probability that this is 0, and I don't really know how to combine those two things. So let's see if we can combine them. So consider this probability. Here I'm going to write what is the probability that y is equal to any y, 1 or 0, given some input x. And I'm going to argue that that's equal to the product of f, the sigmoidal nonlinearity, applied to w transpose x, our model, raised to the power y, times 1 minus f, the sigmoidal nonlinearity, applied to the model, raised to the power 1 minus y. So notice here, this term has been brought down here, this term has been brought down here, and I'm raising this to the power y. What is y? The class label. And then this has been raised to the power 1 minus y. Now, why does this embody both of these here in terms of a maximization or a minimization problem? Well, let's see. So let's consider the case where y is 1 for this label right here. And let's consider the case when w transpose x returns 1. So that means, f of w transpose x returns 1, which means I've applied the model, I've shoved it through the nonlinearity, and it gave me a value of 1. Well, then this will be 1, this whole thing in the square bracket here. Good. Now, let's move over to here. Let's consider the case when y is 0. That's the class label here associated with this line right here. And let's say that the model predicts 0 here for also. So I took my data, I shoved it through the model, I shoved it through the nonlinearity, and it returns 0. So now I have what? 1 minus 0 to the power 1. That's 1. Good. So when this model output agrees with this label, 0 and 0, and this model output agrees with this label, 1 and 1, the product is 1. Ah, that's very cool. Very nice. Now, let's consider the case here where the model says something different than the predictor, than the class label. So y is 1, that's the label, but let's say that the model pushed through the nonlinearity returns 0, well then that's going to be 0 and the whole thing gets annihilated, right? Because I'm computing a product here. All right, let's consider the other mistake. The label here is 0 as before. I have a 1 predicted here, that's the wrong output. 1 minus 1 is 0, and then the whole thing is 0, and the whole probability gets 0. So this really elegant equation does something really interesting. Regardless of what the class label is, I'm going to predict 1 when the output of the model agrees with the label, and I'm going to predict, and then the probability will be 0 when they disagree. And that means I can maximize that probability. And that's exactly what I want to do now. All right, so here's the probability when we want to maximize. Regardless of the label, for a particular input, I want to maximize the model pushed through the sigmoidal nonlinearity raised to the power y, the class label, times 1 minus the model prediction pushed through the nonlinearity to the power 1 minus y. Now this is just for one data point, of course, and I have a bunch of data points, n of them, let's say. And so I'm going to maximize the product of all of these probabilities. So I have the product from I equals 1 to n, the probability that y is equal to the ith label given the ith data. And now I can just write that by substituting this back in as the same thing. F of w transpose x to the power y, 1 minus f of that to the power 1 minus y. And now what I want to do is maximize this. This thing is called the likelihood. And if you've heard of maximum likelihood estimation, that's about what we're going to do, but we're not going to go through all the details of it because it's somewhat outside of the scope of this class. But underneath logistic regression is a maximum likelihood estimation. Now, so now we have an objective, right? This is good. We know what we want to now maximize, which is this product here. Turns out maximizing products is a nightmare, but maximizing sums is a little bit easier. And when you have a product and you want to convert it into a sum, you do what we always do, which is we take the log. So now what I'm going to do is take the log of the likelihood, which is the log of the product, which is the sum of all of the terms here. So now I've got the sum of y sub I times the log, because the log of something raised to a power is that thing times the log, plus 1 minus yi, that was the power that you saw over here, times the log of this thing here. So now I have a maximization of the log likelihood. Now, if we had more time, I would go through how to do this maximization, but we don't. So instead, what we're going to do is I'm going to just tell you that there are built-in mechanisms for maximizing that log likelihood. They're not actually particularly complicated, and if you want to dig into it, you can look up how maximum likelihood estimation works and its related technique called the maximum a posteriori maximization. But here what I'm going to tell you is that there's a logistic regression built into Python and really, frankly, every other programming language, and it takes your data. There's the x matrix and the y vector. X is the data, x0, x1, x2, x3, x4, x5, up to xm. Y are the class labels. And it will maximize that probability by taking the data, putting it through the linear model, shoving it into that sigmoidal nonlinearity to guarantee that the outputs are bounded between 1 and 0. And that it will give you a model out here, and then I can print a bunch of things associated with the model. What were the predictions made? How accurate is the model? And let's go ahead and look at that output right now. So remember, we have a bunch of class labels, 1s and 0s. This is the same class labels that I used for the previous example in the previous session. And these are the output with a little bit funky formatting. So the first 10 labels are 1, that's correct, and the next 10 labels are 0. So this actually got perfect classification. This is the score between 0 and 1, 0 being you failed, 1 being you're perfect. And this is the confusion matrix. Remember, I have 2 classes here. I have 20 data points that are in class 1, 20 points in class 2, and it's telling me that I didn't confuse anything because in the off diagonal there are zeros. This is probably the most important thing you need to look at, which is the precision, the recall, and F1. The support just tells you how much data you have. And these, of course, are the 2 classes here. So let's talk about what these various things mean here, precision, recall, and F-score. This, by the way, is a perfect classifier. This is why everything is a 1 here. So when you build these classifiers, you can quantify their accuracy in a number of different ways. And perhaps the most standard way to do that is with precision, recall, and the F1 score. So let me just go ahead and define that. This is our problem. We have 2 classes, a positive class and a negative class. I have arbitrarily said which class is positive. I could have picked one or the other. It's just whichever one you want. The precision is the true positive rate over the true positive plus the false positive. All right, what's the true positive rate? The true positive rate is how many things in the positive class got classified as being in the positive class. And the false positive rate is how many things that are in the negative class were predicted as being in the positive class. Okay, so that's the precision. The recall is the true positive rate divided by the true positive plus the false negative. We already know what true positive is. how many of the blue points got classified as blue. The false negative is how many things in this class got classified here as a negative. So I misclassified. So think about it this way. The false positive is I took something from the negative class and put it into the positive class. The false negative is something I took in the positive class and shoved into the negative class. And is one mistake better than the other? Well, it depends on what the classes are. If this class is I've detected cancer and this is a class that says I didn't detect cancer, well, both of those mistakes are pretty bad. Telling somebody who doesn't have cancer that they do have cancer could lead to false treatment. Telling somebody who has cancer that they don't have cancer could be bad because we missed something. On the other hand, different types of classifiers may have different sensitivities to making a mistake. If you're using a classifier to predict whether somebody's at high risk for committing a crime and you're going to incarcerate them, well then we probably want to err on the side of not saying somebody's high risk and taking away civil liberties versus saying somebody is high risk and freeing them. That's our model of jurisprudence here in this country. So in any case, we look at precision and recall, and then F1 score is a way of bundling those two together. And it's the product of the precision and recall divided by the sum. I should mention that precision and recall are bounded between 0 and 1. And so when you have a perfect F1 score, it is 1. And when you essentially have a chance classifier, the F1 score is 0. So imagine precision and recall are each 1. Precision and recall are each 1. So this ratio here is 1/2. I multiply by 2. And then I've got a perfect classifier. If precision or recall is 0, which means everything here got classified as being here or vice versa, well then the classifier just failed and you have an F1 of 0. And then of course there is everything in between. So logistic regression is essentially a version of least squares. It's actually a version of maximum likelihood estimation, which itself is a version of least squares, where we take the output of our model, in our case it was a linear model, and we shove it into that sigmoidal nonlinearity. And because of the shape of that sigmoidal nonlinearity, we are guaranteed that the output is bounded between 0 and 1. But we're not guaranteed that the values are 0 or 1, because we had all that stuff in the middle, right? But that stuff in the middle actually is sort of meaningful. Why? Because we're treating that sigmoidal nonlinearity as a probability. So when your output model is output of 1, high probability of being class 1. When your output is 0, high probability of being class 0. And if you're in between, guaranteed between some 0 and 1, it's uncertainty. Right? And that's actually not a bad thing. That's a feature, not a bug. So if my model prediction says 0.5, I should say, I don't know. Now, you could also say, well, put a threshold at 0.5 and everything greater than 0.5 is class 1 and everything less than 0.5 is class 0. But I think uncertainty is okay. There are going to be times where certain data points are just unknown. And because of the nature of that sigmoidal nonlinearity, we can now associate a probability with each output class output. And that is different than the least squares, because the least squares, we had values greater than 1 and less than 0, and so probabilities didn't make sense. But with that sigmoidal nonlinearity, we could make sense of it. Now, I could have done something a little bit harsher. Instead of a sigmoid, I could have done a step function that was 0, boink, and then 1. Now, that would have actually done a hard classification, and we will see that when we do neural networks, but it also makes the optimization a little bit trickier, which is why logistic regression sticks with that sigmoidal nonlinearity.